Myself, Benilda, Assistant Professor in the Department of Artificial Intelligence and Data Science at Sri Muthukumaran Institute of Technology. Today we are going to see the subject 3D Printing and Design. The subject code is CCS 331, Regulation 2021. In the previous video, we have seen processes of 3D printing like extrusion-based, wire-based, granular-based, and lamination-based technologies. In this video, we are going to see about photopolymerization and graphene. What is photopolymerization? It is the 3D printing process that uses UV light to harden a liquid photopolymer resin layer by layer to form a solid 3D object. When UV light strikes the resin, a chemical reaction occurs that converts the liquid into a solid precisely where the light is applied. 3D printing materials include polymers, photopolymers, metals, ceramics, paper, composites, sand, and biocompatible hydrogels, enabling applications from rapid prototyping to medical and industrial manufacturing. Next, we can see about the material overview. This 3D printing supports a wide range of materials, allowing it to be used across engineering, medical, architectural, and industrial applications. The choice of material depends on the printing process, required properties, and end use. First, plastics or polymers. These are the commonly used materials in 3D printing. Example, ABS, PLA, polycarbonate, nylon, etc. The properties are lightweight, easy to print, and low cost. The applications. This is used in prototypes, consumer products, housings, and models. Next, photopolymers, that is resin. This is used mainly in photopolymerization processes. Example, UV curable liquid resins, and the properties are high accuracy and smooth surface finish. Applications, it is used in dental models, jewelry, medical devices, and fine detail prototypes. Next one is metals. Is used for high strength and functional components. Examples, aluminum, titanium, stainless steel, copper. Application properties are high strength and heat resistance. Applications, aerospace, automotive, tooling, and industrial parts. Next, ceramics and glass. Used where thermal and chemical resistance is required. Examples, alumina, zirconia, and glass-based materials. Properties are hard, brittle, and high temperature resistance. Applications are electronics, biomedical implants, and insulation parts. Next, paper and sheet materials is used in sheet lamination techniques. Examples, paper, paper sheets, and metal foils. Properties, low cost and can build fast. Applications, concept models and architectural prototypes. Next, composites and fibers. It's a combination of polymers with reinforcing fibers. Example, carbon fiber, glass fiber composites. Properties, high strength to weight ratio. Applications are structural parts, aerospace, and automotive. Next, sand and construction materials. Used mainly in window jetting and construction painting. Properties suitable for large-scale parts. Applications are casting molds, architectural components. Finally, biocompatible materials and hydrogels is used in medical and tissue engineering. Examples, hydrogels and bioinks. Properties compatible with living cells. Applications are tissue scaffolds, medical research, and regenerative medicine. Next, key concepts for photopolymerization. So there are three key concepts: process, approaches, and mechanism. So first of all, we can see about the process. In photopolymerization based 3D printing, a liquid photopolymer resin is selectively exposed to a light source such as UV laser, that is SLA, and a UV projector, that is DLP. Where the light strikes the resin, it cures and solidifies, forming one thin layer of the object. After each layer is cured, the build platform moves, fresh liquid resin flows over the surface, and the next layer is cured. This continues until the complete 3D part is formed. Next, approaches. There is bottom-up approach. The build platform starts near the transparent bottom of the resin vat and lifts upward after each layer is cured. This approach uses less resin and is common in desktop SLA and DLP printers. Then top-down approach. The build platform starts at the top of the resin vat and lowers down into the liquid resin after each cured layer. This method is mechanically simple but requires more resin. Then mechanism. Photopolymer resins contain monomers, oligomers, and photoinitiators. When exposed to UV light, the photoinitiators absorb the light energy and generate the reactive species that trigger polymerization. This reaction causes the monomers and oligomers to cross-link, transforming the resin from a liquid state into a solid. The curing happens only in the illuminated parts. So next one is key technologies: stereolithography and digital light processing. So stereolithography uses a UV laser to cure resin point by point. It offers very high accuracy and smooth surface finish, making it ideal for dental models, jewelry, and precision prototypes. Next, digital light processing, that is DLP. It uses a digital projector to cure an entire layer at once. This makes DLP faster than SLA while maintaining the high resolution suitable for rapid production of small detailed parts. Next one is applications. So in prototyping and consumer goods, the plastics such as PLA and ABS along with the resins are widely used because they are low cost, easy to print and lightweight. They are ideal for prototyping, product design, models, household items and consumer goods where quick design validation is important. Next, aerospace and automotive. These industries require materials with high strength, heat resistance and durability. High performance plastics like PEK and PEI offer excellent mechanical and thermal properties, while metals provide structural strength. These materials are used for engine parts, lightweight components and functional prototypes. Next, medical and dental. The medical field uses biocompatible resins, hydrogels and titanium because they are safe for contact with the human body. These are used in dental crowns, surgical guides, implants, prosthetics and tissue engineering where precision and biological compatibility are crucial. Next one is graphene. So what is graphene? Graphene-based 3D printing involves reinforcing polymer matrices such as PLA, ABS and nylon with graphene platelets to significantly enhance electrical, thermal and mechanical properties. This is commonly achieved using material extrusion techniques like FDM or FFF. For graphene polymer composites as well as VAT photopolymerization processes such as SLA and DLP. When graphene is incorporated into photopolymer resins. Due to this improved multifunctional properties, graphene-based 3D printed parts are increasingly used in applications including conductive sensors, next one is material selection and characteristics. So graphene nanoplatelets are selected as a reinforcing material because of their high aspect ratio and excellent electrical conductivity, which allow them to significantly enhance material performance even at low concentrations. They are typically incorporated into a polymer matrix such as thermoplastic filaments including PLA, ABS, TPU, nylon, or into photopolymer resins used in additive manufacturing. The polymer matrix serves as a base material that supports and uniformly disperses the GNPs. As a result, the GNP polymer composite exhibits improved tensile strength, enhanced electrical conductivity, and better thermal stability when compared to the raw polymer alone. Next one is process for graphene. So fused deposition modeling filaments loaded with graphene are extruded. Challenges include nozzle clogging and maintaining uniform dispersion. Next, stereolithography or digital light processing. Here graphene is mixed into UV curable resins allowing for high resolution complex geometries and with the conductive properties. Next, selective laser sintering. Here powder bed fusion using graphene reinforced polymer powders are used. Next, the key applications. So electronics and sensors. It is highly conductive, flexible and wearable electronics. Next, structural components. It is a lightweight, high strength parts for aerospace and automotive sectors. Then thermal management. It heat sinks and dissipation components. Then finally, electromagnetic interference shielding. It's a protective housings for electronics. Next one is limitations and challenges. The use of graphene enforced polymer composites also involve several limitations and challenges. Achieving uniform dispersion of graphene within the polymer matrix is difficult, and poor dispersion can lead to agglomeration, which reduces the expected improvement in properties. In extrusion-based processes such as FDM, high filler concentrations may cause nozzle clogging by restricting material flow during printing. Additionally, the high quality graphene fillers are expensive, increasing overall material cost. There are also process related limitations, including a limited range of compatible thermoplastic materials and the risk of graphene degradation at high printing temperatures, which can negatively affect the final material performance. So we have completed the unit 2. The next video we can see the third unit, inkjet technology. Thank you.